have 13 equations, and we know there's 13 unknowns. Okay. Another way to look at it is like, well, let's just, we found those nice 9 equations. Anytime we saw f3 2x in there, let's just plug in negative f2 3x. And the same thing with all these things. So it's actually nicer to think about, these are almost trivial equations. This is Newton's third law, right? So you should almost just already supplement those in the 9 equations. So it's really 9 equations and 9 unknowns, okay? And here's the 9 unknowns, okay? And those are just the forces that the pins, not considering their equal and opposite one, okay? So if you have 9 equations and 9 unknowns, you should be able to solve it. And the best way to do that is to use linear algebra, right? So what you can do is write them in matrix form. And this looks really complicated and crazy, but it's really not. Okay, so what you'll notice is if you write out your 9 unknowns in some set order, okay, and then find out what matrix, when I times this by, will equal the 9 equations. So you look at the first equation. If you go back a few slides to the very first equation labeled number 1, if I times this by this, most of these are 0, but this is 1, 1, and you see that equals 0. Okay, and the number 2 equation was if I times this by the second row, you'll see it equals that. And number 3 equation, this times the third row equals that. And we were very careful with our signs, and we get these from those equations essentially. Okay, so you basically just take your 9 equations and turn them, write out your unknowns, the things you need to solve, and make a matrix, put them in matrix form. And then of course you can invert this matrix. So notice you take this, invert it to the other side, and you know everything in here. It's all geometry, lengths and stuff, and you've done the right signs. And you know everything in here. Of course, everything that you know better end up in here, right? Because the things you want to know are the things you're solving for. Okay? So you do this, and of course, you wouldn't have to do this on an exam, but you might have to set it up. I'm not going to make you take the inverse of any matrix that's greater than 2 by 2 on an exam, but if you did this in MATLAB, which you do in the real world, or some matrix calculator, you would, this is no problem for MATLAB to do. Okay, so you do the inverse, times it by that, and you find all these things. Now, remember from the power equation, you could only find M2. But not only do we find M2, but we also find all the forces that occur at the joints. Okay, and from those forces that occur at the joints, you could calculate what force is going through the beam or the link, and therefore you could know, are they bending, are they compressing or stretching too much, are they yielding, are they buckling, and you could use all your solid mechanics equations for beam bending and those kind of things on each of these essentially link-like beams, and load them and see if they're anywhere near yielding or buckling. Okay. So that power here tells you, the power equation just gets you this, but this approach, although grueling, gets you the external forces and the internal forces at the joints. Okay. Now, what you might say, well, yeah, but this approach is only for static things, whereas the power equation did for dynamic. Okay, and you're right. So far, that's right, but we're going to get to dynamic force analysis. Okay. Before we do, though, I'm going to show you a graphical method. Okay. And that graphical method, whether it's practical to use in reality or not, it will teach you some insights that will be very useful. Okay. Okay. So remember, for the static equilibrium of a rigid body acted upon by a number of forces, say you've got a body that's acting on 1, 2, 3, all the way through n, we know that the vector sum of these forces must be 0. So you know all those vectors, you have to add them all together, and they have to equal 0 if it's static equilibrium. Okay? And by the way, I have to emphasize this graphical approach is, again, for static equilibrium only. Okay? So let's look at this like potato here, this arbitrary rigid link, and say there's 4 forces. Okay, there could be any number of forces, but here you see 4 forces drawn. And of course, the vectors themselves, the force vectors, like I told you, they only contain information about their magnitude, in other words, how long they are graphically, and their direction, in other words, what angle they have from their tail to here, what theta is. That's the only information contained in those vectors. There's no information about where they act. Okay? But say I said they act here. So F2 acts at 2, and F3 acts at 3, and so on and so forth. Okay? If those vectors, or if this potato is truly in static equilibrium, then we know that if we that all those forces summed together would equal 0, which graphically means if you can remember, even though they push on these points, there's nothing in this vector that forces it to be at that location. So you could move these vectors around, and they still, as long as you keep them the same direction, you know, with the same angle and the same magnitude, the same length, you can move them around. And you'll see if you orient them head to tail, you know, or tail to head, tail to head, tail to head, tail to head, that they will make a vector loop that is closed. And you know it's closed because they sum to 0. Okay, now remember, this is not to be confused with kinematic vector loops. That's what we did in topic 2 with the vector loop equation, where we were drawing arrows on the links. And we knew those arrows needed to sum all to 0 if it's a mechanism closed kinematic chain, and that was you know, we could draw the arrows in any direction we wanted as long as we stuck to the convention, and that's how you came up with your vector component things to solve everything, velocity, position, all these things, right? Well, now we're talking about basically a force vector loop. Okay, and for the force vector loops, you have to put them, they can't be arbitrary. Okay, you have to take whatever forces are acting on them, make it in static equilibrium, and arrange them head to tail, so they all go in the same direction, essentially. And like I said, if you maintain their direction, their angle, and magnitude, and put them all together head to tail, if it's truly static equilibrium, meaning if these all add to 0, then you know it'll be a closed vector loop and it'll add to 0. Okay? So obviously, if you take any vectors head to tail, and add them all together, they'll equal 0. Okay? But that's an insight, okay? That if a body is in static equilibrium, you take all the forces acting on that body and you arrange them within a vector loop from head to tail, they equal 0. They must equal 0. Okay, so hang on to that thought. Okay? And so now, the force balance equation does not tell the complete story on static equilibrium. We also need to have an equation which establishes the lines of action of these forces such that the moment balance equation is also satisfied. So remember, it's not enough just to sum the forces to 0. You have to sum the moments caused by the forces as well as the moments, if there are any, and those need to equal 0. Okay? All right, where A is any point on the rigid body. So remember, this points from A to I, and that's a force applied at I. So you can where you pick the moment, where you pick the point to take the moment about is irrelevant, because if it's static equilibrium, they're all the same and they're all 0, right? Okay, under certain conditions, we can determine graphical relationships among the lines of action of the force needed for equilibrium. Okay, so what I'm going to do is I'm going to now show you some different kinds of members, like 2 force, 3 force, and 4 force members, okay? You know, as well as 2 force and moment members, okay? And I'm going to teach you some principles that you can memorize here, okay? And deduce. And this is kind of fun. This is kind of logic, okay? So say we have, so this is a 2 force member, okay? Meaning we've got some member, some link, and there's 2 forces acting on it, okay? And suppose we don't know these 2 forces. I'm just showing 2 blue forces here. Say we know, here's the potato. We know one force acts here. We know one force acts there. So we know the points where the forces are being applied. Tell me, can we know what the line of action is of those 2 forces? Meaning, you know, the line of action of this force is there. The line of action of this force is going through the arrow here. But those aren't right. If you sum these forces, there's no way you can ever sum them so that they equal 0. If there's just two forces and they're pointing in those directions, there's no magnitude you could get unless those two forces have a magnitude of 0 each that add to 0. But then there's not really two forces. You know, a force with 0 magnitude is no force at all, right? So you can deduce that whatever those forces are, their line of action has to intersect both those points. Okay, so if you know the forces act at 1 and 2, and there's just two forces, for them to cancel each other out with finite magnitudes, they have to both point along this line of action. That's principle number 1. Hopefully you can deduce. Okay, and then if I gave you the magnitude and sense of this, in other words, you know, which direction it's pointing along the red line of action. So that's what sense is. Okay, so I gave you the magnitude, the length, and I told you it's going in that sense, okay, that direction along this line of action. Then you could deduce that the one acting at 2 must be equal in magnitude but opposite in direction or sense along that same line of force, okay? So that's the only way these two can cancel each other out, and this can be in static equilibrium. And notice, of course, their moments would also be 0. Okay, the moments caused by both of them, regardless of where you pick the point, will be 0. Okay. Okay. So the two things you need to know for a two-member force is, you know, one that only two forces are acting on it, but really you need to know the 2 points of application, and then you need to know the magnitude and sense of F1. Or one of the forces, and then you can deduce the magnitude and sense of the other one. And of course, you know their line of action intersects them both, and they're equal and opposite. Okay, so nothing too complicated. Okay, now let's look at 2 force and 1 moment members. Okay, so this is, pretend you know there's a potato, 2 forces are acting on it. You know the 2 forces act at 1, and then the other one acts at 2. And you know there's also a pure moment or a couple on there. Okay, okay, so say, I'd also have to give you more information. Say I say the force acting at 1 has a line of action that goes off in this direction. And the reason it doesn't have to intersect 2 is because there's a moment acting on it. So, you know, think about it. That's only true if it's just 2 forces. This is 2 forces and a moment, an extra moment or couple applied to it, okay? Okay, so if I told you this, then you would know, regardless of the magnitude and direction or sense along that line of action that I gave you there in red, you would know that the line of action through 2 would have to be parallel. If it's not parallel to it, then whatever those forces are, they're not going to be able to sum together and equal 0. Okay? So hopefully you can deduce that. So if you have 2 forces and a moment acting on something, and I give you the 2 points, and I give you the sense of one, or the line of action of one, you know the line of action of the other one has to be parallel to it. Okay? And then I give you the magnitude and direction of one. Now you have everything you need to know to find everything else. Okay? Obviously, the magnitude on 2 has to be equal and opposite, like that, equal in length and opposite in sense, so that the forces all sum together equal 0. That would be the case if I add the 2 x components and 2 y components, they equal 0. But also now, you know that the moment, so there's a moment obviously caused by these two things, or if I took the moment about this point, I would take this vector cross that, which would basically be h, the shortest distance between these two parallel lines, times one of these things, f. So fh is the moment caused by that, these two forces. And so you know whatever moment is imparted on it has to equal in magnitude fh, but be in the opposite direction. Okay? So like in that direction. Okay, so again, I reiterate, if you know that there's a moment, that there's a body, and it has 2 forces acting, you don't know where they are, but you know the points of application. So the first thing you need to know is the points of application of the 2 force, and you know the line of action of one of the 2 forces, like, you know, I gave you this red line. And you know the magnitude and sense of that force, magnitude and direction along that line. The rest you can deduce. You know the line of action of the has to be parallel to it. You know it has to be equal and opposite to this force. And you know that moment, that third load that's on this, has to be equal the shortest distance between those two, h times f, and you have to figure out the direction it would have to act to resist the moment caused by the two forces. Okay? And then that is possible to be in static equilibrium. Okay? Okay. So now let's go on to deducing a three-force member. So in this case, say you know on this potato, this member, this link, that there are only three forces. There's no moments, but there's only three forces, and you know that forces apply or are applied there, there, and there. Okay? So, fantastic. That's where you know the forces are being applied. Now, say the other thing you know is that the line of action of 1 and 2 looks like this. Okay? All right. If you knew that, could you deduce where the line of action of the third one would have to be if this is in static equilibrium? So again, I reiterate, you know it's a member, you know three forces act on it, you know they act at these 3 points, and you know the line of action of these two. Can you deduce where the third one would have to be? Well, you know if the forces, no matter what the magnitude is on 1 or its direction, you know it's along this red line, and same thing with the 2. And so you could treat these two as if they're a single force acting at that point, okay, on the body in any direction. Do you see that? So if you have some force here, you could kind of pull them back, because location doesn't matter in vector land, pull them back to this point, and they could essentially effectively act as if there's some force acting at that point in any direction on this body. Okay? So if that's the case, then it's like, well, let's reduce those two forces to a single force. Pretend we get rid of 1 and 2, and we just say there's some force here, and we don't know its direction, but then we know there's a force here. So this now becomes a two-member body, a two-force member body. Okay? So where one of the forces is applied there from these two, and one of the forces is applied there. So you can know the line of action of a two-force member has to go through one of the forces and the other force, okay? That's one way to deduce it. But basically the answer is if you have a three-force member and you know the line of action of two of them, you know the third line of action has to intersect where those two intersect, okay? And you could also deduce, of course, the force couldn't act in any direction but along this to get all three to sum to 0, okay? Or to get the moments to sum to 0. Like, think about it. That's another way to deduce. This line of action has to go through here because, say we take the moment about this point. Well, the moment from this force would be 0, and the moment from this force would be 0. And so, if there was a force in any other direction than along this dotted line, that moment would be non-zero and it couldn't be static equilibrium. Okay? So that's another way to think about it. Remember, we can take the moment about any point we want. If we choose this point, automatically the moment of these two forces is 0. And if this force here points in any direction but along there, the moment can't be 0. It can't be in static equilibrium. So that's another way to deduce that line of action has to intersect those two. Now, what if the line of action I gave you for 1 and 2 was parallel? Well, then those two parallel lines intersect at infinity, and you'd still want this third line to intersect where they intersect, which is at infinity. So you'd make it parallel with them. Okay, so that would be the way to have the third line of action be still intersect the intersection of the other two, if they're all three are parallel. Okay? Okay, and then you could balance things and make it work. Okay? Okay, so again, if I have a three-force member, I know where they're acting. I give you the line of action of two of them. You know the line of action of the third. Now I'd have to give you, what if I give you the magnitude and sense at one of them? Okay, so say I give you the magnitude and direction of this at that one. Now, how do you find the magnitude and direction of the other two? Well, we can use these force vector loops, right? So if we pull this back to there, where they all intersect, which we can do because remember it's still the same direction and magnitude. Okay, it doesn't really have a location in force land. And then we know that the force on this one has to lie, if you draw the force vector, that force vector has to be in that direction. So it has to basically be parallel with it. And to make the force loop, okay, it would have to be this length until it hit this red line. So see how this is parallel to that? This would be the force acting at 3, and we aligned it tail to head, so tail to head, tail to head. And then, of course, on 2, it would have to go tail to head and go all the way there. Okay? So you see, for these to be in static equilibrium, the force vector loop has to equal 0. And so because you know this geometry graphically, you can know how, the direction to draw them in. So they're tail to head, tail to head, tail to head, all going in the same direction. And the magnitude from each of their lines to where they need to point. And then it's much clearer if you draw them acting where they actually act. Okay? So that would be how you would graphically find the magnitude and direction of all those. Okay, so again, what are the things you'd need to know? If I gave you a 3-force member, in other words, some member with 3 forces acting on it, I would have to give you the points of application, 1, 2, 3. I would have to give you the lines of action of at least 2 of them. And then I'd have to give you the magnitude of sense of 1 of them. And from all the rest, you can deduce. You find line of action of the third one that intersects them, or is parallel to both of them. And then you would do, that force vector loop trick, align them tail to head, tail to head, tail to head, and then position them where they need to be. Okay? Okay, so once you have those 3, the 2-force member, the 2-force and moment member, and the 3-force member, you can deduce all other ones. Okay? This is a 4-force member, and you can do 5-force member, 6-force member. So let me tell you, if you can, and this is fairly confusing reasoning, but if you've really internalized what I taught you about the other 3 and memorized those principles, there's really no new principles here. And again, no new principles apply if you do a 5-force member, 6-force, whatever. Right? So let me show you how to use the skills I taught you to deduce this. Okay? Pretend I give you this member, and I say, okay, it's a 4-force member, which means there's 4 forces acting on it. And here's the point of application of all 4 of those forces. And say I give you their lines of action. Okay? Say I give you all their lines of action. Well, there's a couple things we can already deduce from this. You've already given me enough information that I can do something interesting. Okay? And what that interesting thing is I could say, well, let's reduce this to 2-force members. Okay? So think about it. 1 and 4, whatever their forces, whatever the magnitude and directions, we know they're along these dotted red lines here and here. Okay? These guys can be treated as if they are a single force acting where they intersect. But we don't know the direction of that force. Heck, we don't even know the sense of these forces along here. But we know these 2 can be reduced as if they're a single point force there. And then let's take the other 2 pair. We know that these 2 can be reduced as if they're a single force point acting there. Okay? So now we've got basically, we've reduced that pair to that, reduced that pair to that, and now it's basically as if it's just a 2-force member. And you know that 2-force member, the line of action acting at that point and that point would be along this dotted green line. Okay? And that's going to be useful. Okay? So that's one thing we can deduce. Now say they give us the magnitude and sense of 1 of them. Okay? At 1. Say here's the magnitude, the length, and it's in that direction. Okay? Well, now let's treat it as if it's a 3-force member. Okay? Where there's a force acting at 1, which of course we know. There's a force acting at 4, and then there's a force acting at, say, 2 and 3. Okay? Sorry, the combination of 2 and 3, which is right there. Okay? So say we're going to treat this as a 3-force member, 1 acting there, 1 acting there, and 1 acting there. Okay? Then we can do this triangle trick, using the vector loop. If it's static equilibrium, you can pull this back to that point. Okay? Align this okay, with this, because you know the force acting there is essentially, it has to be along this line of action, so it's got to be parallel to this, or this has to be parallel to the green line. And remember, it's got to go tail to head, and it only goes to the next line. And then the force acting at 4 would be, from tail to head, closed loop. That would be where these would all act. Okay, so that's how you find the magnitude and direction of all those. So do you see what I did? It is a little confusing. We found the green line by reducing this to a two-force member. Okay, and then once we gave the sense, we reduced 2 and 3 as if it was just there. So now we're looking at 1, 4, and 2 and 3 together as if it's a 3-force member. And we did the triangle trick, the force loop. Okay, and we found the magnitude of and direction of 1. Well, they already gave that to us, but now we know the direction and magnitude of 4. And we know the magnitude and direction of the force acting here with 2 and 3 combined. Okay, so from that we also know the combination of 1 and 4 better be equal and opposite to this one, because that's if 1 and 4 were combined and 2 and 3 were combined. That's how we found the green line in the first place. That would be this one. Okay, so if you move 4 down to there and move 1 back there and add them together, it better equal that. And it better be equal and opposite to that. Okay, because this is the force that would be 1 and 4 together, and this is the force that would be 2 and 3 together, and they're like 2 force members, they have to be equal opposite. Okay? Okay. All right, so now, okay, if we know that's the combination of 1 and 4, so by the way, what we're going to do here is we're going to do the same thing. We're going to treat it as a 3-force member to find the other 2, okay? So we're going to combine 1 and 4 as if it's this, okay? And we're going to move it back there. And now we're going to say, what's the force from 2, right? It better go from tail to head up to 3. And then the one for 3 better go tail to head there. Okay, so what we did is we said, let's reduce 1 and 4 as if it was just acting there. And we already knew that. Okay, and then we move this to the appropriate place and draw these vectors so that they go head to tail, and point to the correct distances, okay, to close the loop. Okay, and now we can move these all. I mean, you can get rid of this because that's just the sum of these two, but we can move those to where they belong, and that's already kind of sitting where it belongs. Okay, so that would be the answer. You found the whole thing. Okay, so let me tell you what you need to know, and then I'm going to kind of retell you some things that might be useful if this is confusing you. Okay, so first of all, if you have a 4-force member, you need to know that there's 4 forces acting on it. You need to know the points of application. I need to give you where the forces are acting. I need to give you the lines of action of all of them, all the red lines. And I need to give you the magnitude and sense of one of them. If I give you that, using all the past logic I taught you with the other ones, you can deduce the magnitude and direction of all the others. Okay? And remember, the way I did that, you didn't have to do it that way. Like you could have, remember we drew this green line where we lumped 1 and 4 together and 2 and 3 together and did a 2-force member. You could just as equally lump, say, 1 and 2 together. Here, let me clean this up. Just go back here. Go all the way to the back. You could lump 1 and 2 together and see if these two act together, it would be as if it was a force there. Lump 3 and 4 together and see if there is force there, and draw a green line through there and do the entire logical process coming from a different approach. Okay, so there's different ways to think about it, but as long as your logic is correct and you use these force loops that equal 0, line things up head to tail, and treat things as 2-force members and then 3-force members and all this magic, you can get these things, and you'll get the exact same results, of course, because if you have these things, I give those to you, the answer better always be the same. There better always be the same magnitude and direction of all these forces. Okay, so it's in static equilibrium. Okay. Okay. All right, so that's about as confusing as this lecture gets here, yeah, you need to be pretty good to be able to deduce those. And imagine if it was a force thing. You have to be really good and reduce them to different kind of chains of logic. So, but it's all the same kind of principle. Now I'm going to show you an example of how this would actually apply, what you'd actually use on an exam. Okay, the graphical method. Okay, so suppose, okay, that you had, say I gave you this problem. Okay, again, it's another 4 bar, but say a load P shown there pushes